Hi, welcome to lecture 4.2 of the SAGE-based course on Monte Carlo methods. We just looked at continuous random variables, the definition of a probability density function, and you were encouraged to look at a video from Khan Academy on the random variable y, which is measuring the exact amount of rain tomorrow in inches, to get into the field for continuous random variables. And we finished off last lecture with a look at the uniform 0-1 random variable, or the fundamental model, and the AB parametric family of uniform AB random variables that are uniformly distributed within an interval a comma b. Now let us look at expectations. The expectation of a random variable capital X is also known as the population mean, the first moment, or simply the expected value of x. It's denoted by E of x, E for expectation. Okay, it's denoted by E of x. And what is E of x? It's the expectation, and it's defined as the integral of x little d capital F of x. Now what is little d capital F of x? This is for a continuous random variable, it's simply f of x dx. Okay, so the integral x d f of x is integral of x f of x dx if x is continuous, and it is nothing but the sum over all x multiplied by f of x if x is a discrete random variable. So if it's a discrete random variable, we simply multiply the values x can take with its probability mass function and sum over all possible values x can take. And if it's a continuous random variable, we integrate x with respect to its probability density function over the entire real line. So that's all expectation is. Sometimes we denote E of x by ex for brevity, for shortness of notation, where we ignore the parentheses. Thus, the expectation is a single number summary of the random variable capital X and may be thought of as the average. So in general, though, we can talk about the expectation of a function g of a random variable x in the following way. We talk about the expectation of g of x as the integral g of x df of x, which is nothing but the integral of g of x little f of x dx if x is continuous. Okay, or we think of it as the sum over g of x times f of x summed over all x if x is a discrete random variable. And so here little f of x is the probability mass function of the discrete random variable, and here little f of x is the probability density function for the continuous random variable. So we say that the expectation exists if the integral of the absolute value of g of x df of x is finite. Okay, so we do have examples where expectations simply don't exist because they do not satisfy that the absolute value of the integral is finite condition. When we are looking at the expectation of the random variable x itself, we have g of x equals x. So in other words, we can think of the definition of an expectation for a random variable for any function g, and when g of x is simply the identity function, g of x is simply x, then we can now think of the expectation here as being the expectation of the identity function. Okay, so that's just generalization. So thinking about the expectations like this, you can see that the familiar variance of a random variable capital X is in fact the expectation of this function, where g of x is the function x minus expectation of x the whole squared, right? Because you can now write the variance of x as the expectation of this g of x, where g of x is x minus expectation of x the whole squared, and this is nothing but x minus this with respect to the PDF if f is if the random variable x is continuous, and the probability mass function if it's discrete. Once again, variance of x, or in general any expectation, is only defined or said to exist if the integral of its absolute value is finite. Another term is the standard deviation. It's denoted by little sigma of x. So what is that? That's nothing but the square root of the variance of x. Okay, so that's called the standard deviation. And when you think about it, variance is simply a measure or spread of the random variable or its distribution, right? So what is it? It's measuring the expected squared deviation from its expectation. So variance is nothing but the expected squared deviation of a random variable from its expectation. And that's a measure of spread, and the standard deviation is simply the square root of this expected squared deviation from its expectation. The kth moment of a random variable is another definition. It comes from the expectation of the function g of x given by x to the k. Okay, so expectation of x to the k, or it's called the kth moment. It's nothing but the integral of x to the k df of x. So the kth moment of the random variable x, and the kth moment is said to exist. The kth moment of the random variable x is said to exist when the expectation of the absolute value of x to the power of k is finite. Now, having defined various expectations, let's look at some of their properties. If the kth moment exists and if j is less than k, then the jth moment also exists. Okay, so if x1, x2 up through xn are random variables and a1, a2 through an are constants, say real numbers, then the expectation of the sum as I goes from 1 through n of a sub I multiplied by x sub I is simply the sum of a sub I times expectation of xi's. So in other words, the expectation goes through this summation. Okay, and that's simply a consequence of the definition of expectation, namely it's an integral operator and you can take it inside the summation, the finite summation. The third property is if we have n independent random variables x1 through xn, then the expectation of the product of x1 times x2 up through xn is equal to the product of the expectations. Okay, so this again is a property of the expectation for independent random variables. Now, the variance of x was defined above. So if you look here, we define it as expectation of x minus expectation of x the whole squared, but it can be simplified and you get the variance of x as expectation of x squared minus expectation of x the whole squared. That simply comes from completing the square. Now property 5 is if a and b are constants, then the variance of a times x plus b is a squared times the variance of x. Okay, and this again comes from the definition of a variance. Finally, the sixth property says if x1, x2 up through xn are independent and a1, a2 through an are constants, then the variance of the summation of ai times xi as I goes from 1 through n is simply equal to the sum of the ai squares times the variance of xi. Okay, this property rather. So to fully understand the properties of expectations, you simply have to chase the definitions given above, and these properties are merely consequences of the definitions. If you don't understand exactly how these formulas come about, it's okay. Just remember that these are not magic and they really have a basic logic and behind them. Alright, here is a you try at home, and these are some Khan Academy movies about probability density functions and expected values, so that you can get another angle on the material and some kind of practice videos to get these concepts straight, because I'm simply covering the definitions and the formal theory behind these things. So it's really a good idea to go through these nice examples in the videos. So now let's look at the population mean and the variance of one of the random variables we've seen before, the theta parametric family of the Bernoulli theta random variables from last week. Remember, this was our first model of a discrete random variable. So in other words, the indicator function of whether A occurs or not with probability theta is the Bernoulli theta random variable from last week. And for example, we flip a fair coin and we consider the event that it turns up heads. Since the coin is fair, the probability that the event occurs is theta, which is half. And if we define a random variable x that takes the value 1 if the coin turns up heads and 0 otherwise, then we have the Bernoulli theta equals half random variable to model this flip of a fair coin, right? So we saw that the given parameter theta takes a value in the interval 0, 1. The probability mass function for the Bernoulli theta random variable x is theta if x is 1, 1 minus theta if x is 0, and 0 otherwise. And this was a fancy way of encoding the switch statement last week. And its distribution function is 1 if x is greater than or equal to 1, and 1 minus theta if x is between 0 and 1, and 0 otherwise. So now let's look at some expectations. The population mean and variance of the random variable of the Bernoulli theta random variable comes from sums rather than integrals because it's discrete. So the first moment or expectation is expectation of x is x times the probability mass function little f of x given here. So x can be 0 or it can be 1. If it's 0, little f of x is 1 minus theta, and if it is 1, little f of x semicolon theta, or its probability mass function is theta, and this is 0 times whatever is 0 plus 1 times theta is theta. So expectation of the Bernoulli random variable is simply theta. Now let's compute the second moment. The second moment is simply expectation of x squared, and that's x squared times f of x, so 0 squared times 1 minus theta plus 1 squared times theta, which is 0 plus theta, and that is also theta. Now the variance v of x is expectation of x squared minus expectation of x the whole squared, so that is theta minus theta squared, which is theta times 1 minus theta if you pull the theta out of these two terms. So we can see that expectation of x and variance of x will vary with the parameter theta, right? So the expectation and variance are functions of the unknown parameter theta that gives the probability that x takes the value 1. This is why we subscript the expectation and variance with theta to emphasize that the values depend on the parameter. So we talk about E sub theta of x is theta and V sub theta of x is theta times 1 minus theta. Now we can use Sage to do a simple plot to see how expectation and variance of the Bernoulli random variable x varies with theta. So we've simply defined two functions here, and it simply returns theta. The Bernoulli population mean simply returns theta. It takes theta as input. And the Bernoulli population variance takes theta as input and returns theta times 1 minus theta. And this line, we're simply plotting the population mean as x min and x max take values between 0 and 1. And then we are adding the other plot to the first plot. So this plus equals is actually a plot on plot. And finally, the second plot is the Bernoulli population variance, and we're plotting that in red color. And then finally, we're showing the two plots. Okay, so there we go. The red is the variance, and the blue is the expectation. For every theta, we get the variance and expectations. And right away, you're able to see that the variance is very, very high at 0.5. The variance, in fact, takes the maximum value when we have a fair coin, right? Which makes sense. I mean, you're going to get the most variance in heads or tails if you toss a fair coin.